All right, everyone. 5.3 is what we're going to get started on now, and this is graphing of all those polynomial functions that we've been talking about. And as you can see up in the top right, this is an important week for comprehension when you get to calculus very soon. Okay, so we're going to first talk about, and quite a few of this should feel familiar. All right, some things that we even talked about last week, like multiplicities. But we're going to get into the characteristics of, remember, we're just starting with polynomial graphs. We did all different kinds of functions in the previous couple chapters. So polynomial functions, every single one of their graphs are going to be both what we call smooth and continuous. Right? So what does that mean to us? What does it mean to be smooth? Well, it has no sharp turns. Who can give me an example of something that is not smooth like that in the functions that we've already spoken about and reviewed?
I was about to say circle.
Absolute value.
Absolutely. Very good. Very good. Now, continuous, that means that there's no breaks. Right? So no asymptotes or some of those things that we've talked about, those vertical asymptotes that we've seen from some of those functions that we were reviewing and talking about and even graphing the last couple weeks. Okay. And if every polynomial is both smooth and continuous, then what would its domain be?
Negative to positive infinity.
Very good. We say that it is every single x value that we could possibly think of. That double-legged R stands for real numbers, or in interval notation, as somebody mentioned, negative to positive infinity. Excellent. So again, what does that mean? Well, we could put in anything to our domain, we called it, for our x values, and we will get out some y. And not only that, but it's going to be smooth and continuous. In other words, here's an example of one. That's a specific polynomial that you all should recognize as an x cubed and possibly some other stuff. Okay, so these are the things that we're going to be, fortunately or unfortunately, if you're not good at graphing yet, hopefully you'll get better. We're going to start graphing these things. Okay, so we're going to start by talking about some of the things that we've already reviewed, and that is how to find the x-intercepts. Remember, the x-intercept was when we let y be 0. And our y value, if it's a function that we're talking about, means we set that equal to 0. So we said, what's our quickest, easiest method to solving an equation? That's by factoring. Okay, but to review that real quick, when we set it equal to 0, and it's not in what we call factored form already, where it's got our factors or parentheses, and some of them could be squared or cubed or whatever, then we want to factor that GCF. Okay, we call it the greatest common factor out. Then after that, we'll try to factor using our binomial or trinomial techniques that we've learned since probably junior high school. Okay, then once we have all of our factors set, whether it was something on the outside, stuff on the inside, and even squared or cubed, then we will take each one of those factors, and of course, since the whole thing set equal to 0, we'll set that, and that factor equal to 0. And by doing that, we will have then found are zeros, they call them sometimes, or are x-intercepts. Why do they call them zeros? Pretty obvious. Okay, so just a quick review of that, and something else that we've talked about already, and that is how these graphs behave at the x-intercepts. Now remember, x-intercepts where it's crossing through the x-axis. So if we had some examples where it hit there, there, and there, well, first of all, it'd be nice to know what the degree of this polynomial or equation is. Remember the even versus odd for end behavior? Remember, even was the same, odd was the opposite. And if we knew something about each one of these individually, their multiplicities we talked about, if those were even or odd, it also told us things, right? If this one right here was, let's say, x plus 3, and it was squared, and then the other one was x minus 1, and then the other one was, say, x plus, or excuse me, x minus, I don't know, what does that look like? 5 maybe? So if I made my tick marks, 1, 2, 3, 4, 5, and then this one, 1, 2, 3. You should be able to kind of sketch this out very quickly without using any technology. Okay, the most powerful thing on earth, your mind. Just by looking at these. And whether it was an odd or an even power. Okay, so remember we reviewed that already, but wanted to talk about it again. It will come back when we're graphing these things in more detail. All right, so we'll talk about how the odd will go to the opposite side and therefore cross, and the even will touch and bounce back the same or even same way. Okay. Other than that, another quick review. If we know the degree is n, remember we talked about the number of terms, the number of possible x-intercepts or zeros that we would have? Well, here's some more stuff for your notes if you wanted to pause the video at this point and write some of this stuff down. Otherwise, this is all a quick review of some of the stuff that we've talked about. And now I wanted to see if you can give me the equation of this example based on stuff that we've been talking about and reviewing again. Okay. So again, is this a polynomial function?
Yes,
Why, Julian?
because it's continuous and smooth.
Good. No sharp turns when I put my pen or pencil down. Notice I didn't ever pick it up. That's what it means to be continuous. Smooth because there's none of those sharp turns. And you guys will see why in calculus we cannot have that feature. Not so much in this class. All these topics are just setting you up for the finishing pieces to that in calc. Okay? So what are some obvious key points that we want to look at?
The zeros.
Good. Are zeros or x-intercepts. Because right then and there, we should be able to say that this function has, and let me give myself a little bit more room, 3 zeros, doesn't it? Along that x-axis. Where are they located?
-1, 1, and 2.
Good. But how do we translate that over to this, to our function?
It's going to be x plus 1, x minus 1, and x minus 2.
Excellent. How come? Why did you tell me the opposite when somebody else just told me that it was -1, 1, and 2?
Because you're going to equal it to 0. So then if you're solving for x, it's going to give you -1. And all
Very
that.
good. And as we mentioned before, when we were graphing all those functions, remember we did the opposite for the x's. Remember I gave you that little joke about our x's wanting the opposite of us, and that's why. All right, so that still plays, that still holds true here, but again, for that reason of setting this equal to 0. Here's the problem with this. Right now, what is the degree of this equation?
3.
Right now, it looks like 1, 2, and 3. When we would multiply this all out, we would have an x cubed. Why do we know that cannot be true?
More than
That's
3.
not what it looks like.
Good. That's a good. Why doesn't it look like it? What do we know odd are always going to be?
Opposite.
Opposite directions, where even was always the same, either up or down, with however many humps or whatever, depending on what the actual power is. We'll talk about the number of turns and remind us what we talked about last week as well. So that means one of these things or more has to have a multiplicity, has to have a multiplicity of maybe something even. Because right now we have 3, and that's no good. So look at these zeros that we just talked about, those x-intercepts. And can you see how this one goes from a negative to a positive in the y value? This one goes from a positive to a negative. So what do we know is true about these zeros and their multiplicities? What do they have to be?
Odd
Even?
number.
Oh, no, wait.
Odd multiplicities, right? Because remember, odd, we said opposite. It goes from a negative to a positive. This one goes from a positive to a negative. But notice, what does this one do?
It touches the X.
Good. It goes from a negative to a negative. It only touches the x and goes back the even or same way. Right? So remember, I'm trying to use that terminology again. Odd, opposite, even, same. So I know that these two have to be odd and this one has to be even. But is it 2? Is it 4? Is it 6? 8? Who do we appreciate? I mean, whatever. How about these? 1, 3, 5. What odd power? Well, remember the whole degree. Another thing that we could use was not just the zeros to help us with the degree, but also the number of turns. Remember, there was a maximum number of turns that we could have for this thing. And how many turns are there?
And -1.
Very good. How many turns do we have for this one?
5.
1, 2, 3, 4, 5.
No, it's 3.
Ooh, okay. Remember, I'm trying to get you guys to make sure that you differentiate between the x-intercepts and the turns and all this stuff. It can get jumbled in there. And that's why it's really important to understand this, because the better you do now, easier calculus is going to be when you come across this. This is not a turn. Why do we call it a turn? You're turning into a different direction, right? This is not turning into a different direction. It's just a little kink in our hose here of continuity, okay, of it being smooth. It just goes up here, kind of plateaus, flattens out, and then keeps taking off. In other words, what is it doing from here to there? What's another vocab word?
Increasing.
Very good, guys. Increasing. Excellent. But what does it do at that point? It changes and starts what?
Decreasing.
Does it stop at that point, or does it continue to decrease?
Continues.
It continues.
Very good. So those other values, what we said were turning points. And maybe I should circle this one so that you can see both. There are only 3, which means what is our possible degree of this equation? Very good. Since it was like somebody said in -1, we're saying, well, if there's 1, 2, 3 turning points, then it could be +1. Our degree could be 4. Could be higher, but we know that it's going to be 4, and therefore, because this one was the one that stayed negative, it went the same direction, we're going to put a what at our x minus 2 factor?
2.
Very good. We're going to make sure it's even, and we're going to guess that it's probably 2, because then that would give us a degree of, if we put 1s there and there and keep them odd, a 4. Like we said for our 1, 2, 3 turning points. Now don't forget, this is facing what direction?
Down, so it's negative.
End behaviors are down, so very good. We're going to have a negative value in front. And if you wanted to find what that a value is that we say in front actually is, what kind of equations do we know how to solve? This is in all of mathematics. There's only one equation that we know how to solve.
Linear.
Very good, Barrett. That is the correct answer in one word. I like it. We only know how to solve one equation with one unknown. And right now, this one would have 1, 2, 3 if you had that as your y. And if you wanted to solve for the a, then you would have to know the what?
X and Y intercept.
Good. And do you need both? No, very good. You only need 1 point. N, X, and a Y, so that you can find your A. So if they ever ask for it, yeah, I already got these 3 points. The problem is I already know that those are going to cancel these out to make this 0. So guess what you cannot use to find your A? You can't use these. You already did. And it will give you 0 every single time, which will wipe all of this out, including the A. You need the A, which means you cannot use your x-intercept, which makes the whole thing 0. So what other thing can we use?
Y-intercept.
Very good. We could use this one, which is the point what?
0, 4.
0, 4. And that would allow us to find that A. Okay? So wanted to just quickly go over all of that. Very good for everyone that was putting that in the chat or saying it. I like the participation today already. Okay? So remember, again, another reminder here about our end behaviors. Our end behavior depends on 2 things: the degree of the equation, even meaning what?
Same.
Good. And odd meaning what?
Opposite.
Excellent. But what else matters on whether they're both the same up or both the same down?
The leading term, if it's negative or positive.
Very good. That leading coefficient, they like to say that first A sub n. That's a subscript for naming purposes only. Okay? If it's positive, then we're positive. We're up. If you're negative, you're down. Okay? But the odd ones, a little bit more difficult. We're going to read those left to right. Okay? For our x is getting bigger, increasing. And if it's positive, then we're going to do this. Now notice they didn't put anything in here because we don't know what degree it is. If it's a degree of 1, then it's this. If it's a degree of 3, it could do something like this. If it's a degree of 5, we're going to have even more possible humps or turns. Okay? And so on and so forth. So they don't put it. All we're talking about is the very ends. And remember, the way that we technically should be putting this is not in words. The left is rising, the right is falling. We're going to be putting it more in mathematical terms with these arrows. And we're going to say as x approaches infinity, which means the furthest right, then our y approaches positive infinity. And as our x approaches negative infinity, then negative infinity for our y. Okay, but if it's negative, then from left to right, we're going to be decreasing. Okay, all should be a quick little reminder. Hopefully that rings a bell. Because why is this stuff so important? Okay, let's put it all together. The stuff we've talked about last week and this week in this chapter 5. Remember we talked about from left to right, it decreases. Then it changed to increase, then decrease, then increase. Therefore, what are we going to want to know?
Is it the turning point?
Very good. And why is that turning point so critical?
You can establish the degree, possible degree of the polynomial.
Very good. That is one thing. Excellent. What else? Why are these so critical? See who can put some of the stuff that we talked about even before last week together. Maybe I'll give you a hint. See if that helps at all.
Would it give you the max and min?
Ah, very good. Very good. Annalie, very good. That's excellent. Not only are those going to be where it just turns, which will help us with the n-1 possible, like we talked about, degree of this whole thing, but it will also help us to find those local and absolute max and mins. Very good. Awesome. Now you guys are starting to see it all come together, hopefully. Okay. So we will call these critical points in calculus because they are so critical, can tell us many, many things. And just by looking at this, you guys should be able to tell me a few things. Who can tell me what? I'm leaving it broad.
That it's the same.
Meaning what?
So they're both going in the same direction. So
Even polynomial.
Very good, very good. Corey, you cut out there at the end. Julian helped you out with that lifeline. They are facing on the ends up, which means same direction, even, and it's going to be a positive at the beginning because they're up. Very good. So that's what that's going to tell us. What kind of even? What's the degree possibility? Since we have 1, 2, 3 turning or critical points.
It could be a 4th degree.
Very good. Excellent. How many x-intercepts are there on this one?
There are 4.
1, 2, 3, 4. Which means, do we have any multiplicities?
No.
Good. But remember, it could be higher than 4. All we know is that it's even and positive at the beginning. There could be more than 4. How do we know that even though there are 4 x-intercepts, that we're just going to have x something, x plus or minus something for every one of these? How do we know it's all going to be the first to give us all 4? Look what it does at each one. It goes from one side to the other, one side to the other, opposite, opposite, opposite. So none of these hit and went back the other direction. So again, all of those concepts put together allows us to graph these things and graph them pretty well. And what I mean by that is not just because your drawing's perfectly smooth and curved. What I mean is the placement of these points, and even our y-intercept, which happens to also be an x-intercept. Okay, all those things will help us in order to graph these things. Okay, obviously some things are more important than others. Okay, so we talked about all of this before. We're just trying to put it all together and see how we will use it even in calculus and call it something different. And when we call it something different, that means there's going to be a different way to find it. A much faster way in calculus. Okay, so you'll get there. So here's a little how-to. Remember, I did mention this a couple weeks ago. Even versus odd functions. And this is how we tested. And we said whether or not it was even or odd depended on if we put in a negative something. Did we get the same thing out we originally had? Then guess what? Even. If we put a negative in and we got out the opposite of our original function, then odd. And we said what that meant for us was if it was an even function, it was symmetrical about the y-axis. And if it was an odd function, then it was symmetrical about the origin. And what that looked like was in our original function, we'd have x comma y. Well, then if we also had an odd, it would be negative x, negative y. That's what it meant to be around the origin. Okay, around the y-axis, our original function, we just put in some x, get out the y value. Well, then if we put in a negative x, we get out the same y value. And that's what this is saying. So all the stuff that we've been talking about the last couple of weeks, we're going to try to put it all together and see if we can't sketch this graph. Okay, so I'm going to go ahead and pause the video here and let you guys go ahead and take 3 minutes to give this a shot. All right, try this on your own real quick. All right, I hope you're able to come up with most, if not all of this. Who can help me out? What are some of the things that we should look at right away and be able to say and or graph?
The direction.
Good. Definitely see that negative right from the jump. What kind of degree, what kind of polynomial is this?
Odd.
Good, because there is an x squared here, even though it's factored, right? We have an x squared and then an x to the first. Multiply that together. Not only is it odd, it's cubed. And we already know cubic functions look like this. Or they can have a little bit more curvature to them, more peaks and valleys. But because it's odd, we already have an idea it's going to look something like this. Just by looking at it now. Okay, just in a few weeks, we already can do stuff like that, where normally people would look at this and be, no idea, right? What else can you tell me?
It bounces at the x-intercept -3, and then it crosses at 5.
Good. Those zeros or x-intercepts that I was just given are very easy to find when it's already what for you?
Factored out.
Very good. I like it when it's already factored out because they've done all the work. All I got to do is set this whole thing equal to 0, which means set that factor, and you can even set this factor equal to 0, but remember, that doesn't have an x, so it's not going to give you an x-intercept. Right? So, good. We're definitely going to have one at -3, and we're definitely going to have one at +5. Remember, don't put +3 and -5. You have to set this whole thing equal to 0. And in order to get the back to 0, you're going to have to do the opposite. Okay? So, when we graph this, because we know it is a cubic polynomial, because of the x squared and the x to the first, or degree 3, we know that we would have a maximum number of turns of 2. We also know that because this negative is in front, that we said it would be going what from left to right?
Down.
Down, decreasing. So does that mean I hit this one, go through, hit that one, and I'm good?
No.
Not necessarily. Very good. We have to keep in mind what we call the multiplicities of each of my zeros or x-intercepts. And we said when the multiplicity was even, it would stay on the same side of your y or x-axis. Okay? And then if it was odd, then it would go to the opposite side for your y values, or the opposite side of our x-axis. So when we go to finish our drawing here, we know that we're going to start somewhere up here, come down. Do I go through that value? Do I go to the opposite side?
No.
No, because it was the -3, right? We're going to hit that and go back up the same direction. Now, where do I cross through this? How would I find it?
That f of x to 0, plug in 0 for all the x values.
Very good, Taylor, which means I would actually, and what do we call that? Our y-intercept, right? So that means if we want to find the x, we let y be 0, like she said. I would have my y equals -2 times, what happens when I plug in a 0 here? I just get +3, but don't forget you had to square it. So it's going to become a 9. Right? And then when I plug in a 0 here, I'm just going to be left with a -5. But what do I do with all of those values? What does it say to do?
Multiply.
Multiply it all out. And as you can see, a negative times a negative is indeed going to be positive. Okay, unfortunately, I'm going to do 2 times 5 because that's 10 times 9, which is 90. I'm not going to go all the way up here to 90. Okay, just label it and put 90 so I know you know that that's where our value would be. Okay, you don't need to make 90 tick marks. Okay, is that where it hits and actually goes back down? I don't know. In order to find those, I'm going to need a little bit more. I'm going to need some calculus to find where those max and mins, those turning points are actually located. Okay, so for now, we're just going to do this and get a pretty close representation of what our graph's overall features are. Okay, just don't forget to put those arrows at the end, which means it goes to positive or negative infinity. And does everybody agree with the basic shape of this?
yes,
Didn't we say it would be cubic? But a decreasing cubic going through -3 and 5, or at least hitting them, those values on our x-axis. So again, pretty cool to be able to find as much or as little as they ask for, but being able to see this in our head is huge. Because then we know the number of turning points and critical points are 2 max. All right. So that's almost it for this section. We're going to wrap it up with this thing called the intermediate value theorem, and then review something really important that I've been hitting at, those local and absolute or global extrema. Okay, this one is probably new. And to let you guys all know a little secret about me, I don't know if you guys want to. I should probably pause this recording, but I'm just going to go with it. I was 3 feet tall. There it is. I said it. You guys may not believe it, but I was 3 feet tall. You want to know how I can prove it to you? I'm now over 3 feet tall. I know you can't tell on this tiny little screen, all right? But I am actually almost 6 feet tall. Now I can prove that to you because I was not born over 3 feet tall. So that means if I was born less than 3 feet and I am now more than 3 feet, what did I have to do in that growth? I had to hit 3 feet. And that's exactly what this intermediate value theorem pertains to. Okay, it says that if you have a polynomial function, now, to us, that's all we're going to do in this class. When you guys get to calculus, it won't necessarily just be those that you'll be finding these intermediate values, okay? But it says if you plug in something, anything called a, into your function, and you get out some y value, and then you plug in something else, well, as long as they have opposite signs, meaning that one of your y values came out positive and the other negative, or vice versa, okay? Then what has to be true if one is positive, one is negative? What value had to hit if it's a polynomial function, which we said is smooth and continuous?
0.
Very good. So again, if I plug in some a value and some b value, and a comes out positive and b comes out negative, at some point in between there, doesn't have to be right in the middle, they're calling it c, that value, when we plug it in, would have to come out 0, since this one came out positive and this one came out negative. We had to somehow in between hit that 0 at some point. Does that make sense? And the reason that's so important is, what is this called?
X-intercept?
Very good. This is one of our x-intercepts, also known as a solution, a 0. All those things that we've been trying to solve for our functions to equal 0. So we're trying to combine the algebra and the geometry together. Okay? So this is something that's really important. For right now, you guys only have to worry about polynomial functions. In calculus, it will have to be both continuous and smooth, like we talked about. A polynomial function is. Okay? So, last thing we're going to talk about are these local and global, which we also called absolute max and mins, extrema for plural. Okay? Remember the difference between local and global? Local was around this little neighborhood, this little area of our graph, where the global was the entire thing when and if we extended these. So obviously, locally, around this value right here, it is the highest point. So we say it is the local max. Around here, local min. But this one is both a local and global max because it is the highest point on this entire graph. Do we have a global or absolute minimum for this graph?
No.
I am Ron Burgundy. Why did you
Would
say it
it
like
be
that?
would it be negative infinity?
Okay, good, Lillian. What is negative infinity? Can you graph that for me? So remember, infinities are ideals. They're not actual concrete things that we can touch. So therefore, we never include those, and therefore, you're right on par. There is no absolute or global minimum. And that's because of those things right there, those arrows. Okay, if I cut it off and I didn't have the arrows and I only had dots, then would we have an absolute?
Yes.
Yes, and could one be even up here? Well, now it's just this one, not both of them. Okay, and if I cut it off here and there, is this a local min? You remember us talking about that a couple weeks back? Would this be a local minimum if it was an endpoint there?
No, because it's an endpoint.
Very good, Lillian. We do not know what happens to the left of this. Does it hit that and go back up? Or does it keep going down at this way, this way? We don't know. And we can't speculate, we can't guess. So if there's ever an endpoint, it can never be local because you don't know what's going on the other side of this. Only this you do. Okay, but an endpoint can only therefore be an absolute or global max. So if you want to make a note of that, do it. All right? Okay. Then let's move on to the last two sections for today. That's the long one for sure. Okay, we're going to talk about dividing these polynomials. And before we get into dividing polynomials, I wanted to ask if you guys knew how to do long division with just numbers. Do you guys remember how to do that?
Yes.
Yeah.
Okay.
Until I did the homework.
It's been a while, right? And so that's why I'm going to bring it back to you all real quick. And does anybody know how to tell if a number is divisible by 3? There's a few rules. Obviously, 10 is easy. It has to end in a 0. 5, a little more difficult, but still easy. 5 or 0, it has to end in. 2, also pretty easy. It has to end in a 0, 2, 4, 6, or 8. It has to be an even number. But what about the odd number, 3? Does anybody know the rule for that and how to tell if a number is divisible by 3? And isn't that pretty crazy that we don't? And we're in pre-calculus in college, and we don't know how to tell if a number is divisible by 3. So this is going to help you to understand a little bit about those division rules, but more so about dividing polynomials, and then we'll actually get into that. So help me out. A few people shout out some of your favorite numbers or digits.
9.
10.
Not everybody at once.
7.
Oh, I was going to say, did I hear an 11? All right, just give me like 1 or 2 more.
51.
I hear 22 and 51. Okay, that's a little bit more than I wanted, but we'll go with it. Here's my point. Is this number divisible by 3? Well, what does it mean to be divisible? Because you can take any number and divide it in, but it doesn't always go in what? Perfectly, with no remainder is what we mean. Yeah, very good. So check this out. It's really, really cool. All you got to do is add up all of the digits of any size number. And if that number is divisible by 3, then so is that. So let's add them up. 10. There's 9 and 10. So we got 20. And then these two would be 7. Don't go grab your calculator. All right, watch this. What is this number? Looks like my bank account. 91 million. Just kidding. 72,251. Is that divisible by 3? Well, remember what we always do. We start with the first digit and forget about the rest. And we say, what number times this gives me that or less? Right? And we know you guys have done this, but it's been a while. 3. We put it right above. Then we take that number and we multiply and put it right underneath to see if there's anything remaining. And if there is, cool. If there isn't, we move on and we bring down the next thing. And then we say, all right, well, now this is the digit that we're looking at, or this is the quantity that we're looking at. And does 3 divide into that? No, we put the placeholder that we subtracted, and now we bring down the next thing, and now we have 10. And we know that 3 goes into that 9, which gives us 1. Bring down the 7. You guys get the idea, right? I'll kind of jam through it now. 5, we multiply, we subtract, we bring down the next. We multiply, we subtract. What do you notice are the only things that I'm getting since I'm dividing by 3? What kind of leftovers?
Everything under 3.
Very good. Either a 0, 1, or 2. You shouldn't have 3 or more because otherwise you should have done another multiple of 3. Okay, good. All right, now I bring another 2. Goodness. Why'd you guys save so many numbers? 5. Did I do this right? 2, 2, 5. I missed something. Too many numbers.
Should have been 12 instead of 22.
Yep, should have been a 1 there. Thank you. 12. Just gonna make this different and this different. And this different. All right. Let me make sure I had that right. Okay. So that was 12. So now we're gonna have 4, which is 12. And then we bring down the 5. And then 1. When we subtract 3 from that, we get 2. And finally, with your big old ginormous number, you can see that not only does it divide in, it divides in evenly with no remainder. Now, the really cool thing is if I would have put a 2 at the end of this and we would have done it again, we would actually have had a remainder of 2. And if I would have added all this up, we would have had 29. And I know 3 goes into that 9 times, right? Which is 27. And notice I'd have a remainder of 2. So there's all kinds of cool tricks, but this process that you did in maybe what, 3rd grade, 4th grade, is the exact same process we use with polynomials. Polynomials are obviously just a whole lot uglier because they have x's and numbers and powers and all that stuff involved. Okay, so there's 2 different types I'm going to go over with you. Okay, one is called long division, which you can assume that that's exactly what it is, long. And then this other one is synthetic division, which you guys know synthetic is like a man-made thing, and somebody created this shortcut. Okay, now notice the problems on the left and the right are the exact same. So I'm going to start by doing long division, and then I'm going to show you this cool shortcut called synthetic division. And I want you to see the relationship between the two. because you can only use synthetic division certain times. And therefore you have to also know how to use long division. Okay, so check this out. Make sure that you know how to read. And what I mean by that is we read left to right and top to bottom. So this says take x cubed minus 3x squared plus 5x minus 6 and divide it by the x minus 2. Now this is what's a little bit weirder than what we just did with numbers. We usually only divided by a single number, whether it was 3 or even something more difficult like 13, but it was one thing out there. With polynomials, by definition, poly meaning many, nomial, name or term, we now have two things that we're going to divide in. And that's going to be hard to just do it into one. But check it out. The process is the same. I'm going to first look for something times this that gives me the first thing or less. I'm not going to worry about the rest yet. Now, because it's x minus 2, and I'm only going into one thing, the first term, I'm going to just focus on the first term as well. So what times x is going to give me an x cubed or less?
X squared.
Now, that's usually the easy part. Very good, Julian. Here's where most people screw up. Watch this. What do we do next? When we put the number up there, what did we do with it next? We took it and we multiplied to whatever was on the outside and then subtracted to see what was left. What remained? Well, then that means since there's more than one thing out here, that's why I put the parentheses, even though you don't need to, I'm going to have to take this and I'm going to have to multiply to both of those. That's not where people make a mistake. You know x squared times x is x cubed. And that's our goal, is to always get whatever's there so that it cancels out. But don't forget, you also have to do the x squared times the -2, which again isn't difficult. Everybody good so far? Taking this, multiplying just like we did, and that's what we get. But this is where this was easy up here, because then we just put subtract. And we found what was left or remaining. That is the #1 issue that students make when doing long division, is right here, this step. You guys ready for it? They do that. And that's wrong. Why is that wrong? What are you supposed to subtract?
The whole equation?
Very
I'm not
good.
sure.
Yes, excellent. Very good. That means you can either do this and have to distribute it, or just distribute it. But keep in mind, guys, this is the #1 mistake that is made right here, is people just put the minus out in front because that's what they've done since elementary school. You have to make sure, like, I don't remember who said it, I couldn't see. You have to subtract the whole thing. That means a negative times a negative, that will become positive. And is that going to change your problem if you don't do that? Heck yeah, you're going to have the opposite of what you should have. Okay, so again, make a note of it, be careful, make sure that you distribute the whole thing, because now you can see what's left is a -1 x squared. And just like before, we'll bring down the next thing and do it again. And by do it again, I mean go back up here, say what times this first thing gives me that thing. And any takers?
-x.
Good. Now, how do you know it should be -x and not x squared? You already had that up here. And what do we always write these in?
Descending order.
Very good. So if this was the power of 2, which, by the way, if you took all of this extra stuff in my polynomial and just took the degree, x cubed, and you divided it by just the biggest thing here, what is x cubed divided by an x? it's x squared. So you should already know what you should be starting with. There just may be a coefficient that you have to worry about as well. Okay, so negative x, careful, times the x, negative x squared. That's what we wanted. Negative x times the negative 2, we just have to do positive 2x. Then don't forget, you have to subtract and subtract both of those things, the whole term, to cancel out the first. We're left with that. Bring down the last thing, which means this is our last attempt to see if it goes in, like Barrett said, nicely, no remainder. And we will then focus on, what times x gives me 3x?
3.
Good. Positive or negative? Does it matter?
Positive.
Very good. Positive 3 times x gives me my 3x. I always want to get exactly what I had because I know I'm going to subtract to cancel it out. Okay. But don't forget the positive 3 times negative 2 works out really well. That is also negative 6x, which means I know when I go to subtract them, that and that will become the opposite and cancel everything out, which means no remainder, which means this right here divides in nicely, which also means that this, my friends, is what is called a factor of this. I could actually write this times x minus 2, and guess what it would give me? Back my original. And if you notice, I have something like this, a trinomial we called it. If I can take this and factor it, and I have this, which I already know goes in evenly, which is a factor, then I can start setting these things equal to 0 and finding all the zeros or x-intercepts, which will help me to graph when it's not in that nice factored form like we saw earlier. Everybody cool with that? Well, then check this out. This is really cool. Make sure that you watch closely so that you understand, because it's going to be really weird. Okay. What makes this so long is all the variables. If I could get rid of all of these x's, right? If it was just that easy to just get rid of all the x's, right? Then we'd just be left with the numbers. And notice the numbers were the only things that we're really focusing on, those coefficients. So all we're going to do, first things first, always make sure that whatever the degree is, that you have everything all the way on down to 0. So notice I have 3, 2, 1, and then x to the 0, because that is just a 1. And therefore I have everything accounted for, and it's all going to line up nicely so that we could actually add and subtract, because I don't want to do this anymore. But remember, one thing I told you, the only time that you can use synthetic division is when you're dividing by an x minus something. It has to be a 1 in front of that. Okay? If there's a number in front, there was a 3 here, then you would have to use long division. Okay, and that's not entirely true, but for our purposes, it's not worth trying to do synthetic division if there's a number in front. Okay, trust me on that. I'm going to leave it at that. Okay, so all I'm going to do is I'm going to take everything that I see here, but not the x's. And how many x cubes do we have there? One. How many x squareds? -3, +5, and -6 ones. And I'm going to take just what are called the coefficients. So I'm going to have a 1, -3, 5, and -6. And this is what I'm going to divide with, rather than all those x's. But What am I going to divide by? Well, if I got rid of this x, remember, Taylor asked a good question. What if the coefficient is a -1? Then it's a -1. The only thing that really matters is not the numbers per se. That's just what we deal with. It's the variables that we're trying to get rid of. Okay? But what we do over here is, what if we get rid of this? Well, then -2 would be what we would use over here to divide. But remember the whole process. And the one key thing that I told you most students make mistakes on with the long division is with the subtraction. And when we subtracted every single one of these, what did they become? What one word am I looking for? The what? Good, Barrett. He mouthed it to me. The opposite. So what we're going to do is we're going to actually, so that we can add these things rather than subtract all of these things, is we're going to take the opposite of this. And we're going to say it's going to be a +2. Okay. Now, once we have this set up, it goes really, really fast. So I'm going to make sure that everybody understands this setup so far before I move on and actually start doing this. All I did was drop. Once I knew that I had my power of 3, 2, 1, and 0, then I took their coefficients and I wrote those down. Then I took the opposite of this, because that's what would equal 0, is the x equals 2. And that's what I'm going to use as my dividing piece out there, so that I don't have to worry about subtracting and losing anything. Now I'm going to just be able to add, since I already did the subtraction, basically. And what we need is something to start with. So whatever is in this first slot here, you're just going to always bring that one down so that I have something on the outside. And what do we always do with the things on the outside?
Multiply.
That's right. We're going to continue to do that. Good, Alex. I will take the 2 and the 1 and I will multiply. But where did we always put the stuff when we multiplied them on the outside?
on the inside.
We put them underneath these on the inside. Very good. So when I do that 2 times 1, I'm going to put the 2 right there. And do I need to subtract the -3 and the 2? No, we already took the opposite. We already did the subtraction for all of these. We already changed them to the opposite. So I'm just going to add that column just like I did here. Literally right here. Do you guys see it? Same numbers. And what do I get?
-1.
Be careful with your signs. You guys would be laughing at how many times people just make a silly mistake like that. Unless it's you, then you're not laughing usually. Okay. Be careful. -3 + 2, -1. Now, what am I going to do with that -1? I'm going to take the 2 and multiply, and then I'm going to write it underneath the next thing on the inside. So now I got -2 times my, my +2 times my -1, which is -2. Add straight down. Do it again. Now what? 2 times 3? 6. Add straight down. I always like to put a little half box there as well, because what does that last column always represent if there's nothing else to bring down?
Remainder.
That represents your remainder. Very good. Now, obviously, you guys can see how much simpler this is than this. But what's weird is this up here was our answer. As is. What the heck is this? That doesn't look like our answer. But remember, at the very beginning, we got rid of all of our x's and just took the coefficients. So then guess what we have to add back in to give the answer.
The X's.
But how? With what? Well, remember up here, we had x cubed and some stuff, and we were trying to divide it by x and some stuff. And we said that x cubed divided by an x would be x what?
Squared.
And then everything on down to none. Our descending order. And hopefully you can then see that our 1x squared minus x plus 3 is the same here as it is there. But this, a whole heck of a lot cleaner, that's for sure. A lot less places to make a mistake, but you don't see a lot of the mistakes because of that. Right? Hopefully you guys understood the process there. If not, we can go over that, but that's what that entire section is about. Okay, 5.5 is using it. And how are we going to use that? All right, so 5.5 is called zeros of polynomial functions. And why is it called a zero? What do we say it also represented?
X-intercept.
Very good. Also called a solution to our equation. You guys are doing it well today. So, a few things I need to just kind of talk you through, and when we'll wrap it up here so you guys can start working on that group quiz, okay? There's a thing called the remainder theorem. What do you think that pertains to?
The remainder.
Very good. All we got to figure out is in what way, right? So it says if you have some polynomial and you divide it by this, just like we did up here, the x minus something, well then if there is no remainder, then what does it mean that this is to that?
A factor.
Very good. So the remainder theorem and the factor theorem go hand in hand. Okay, they both are virtually finding the same thing. Okay, if we divide by this thing, then it will give you the remainder. That's why it's called the remainder theorem. So whatever this is, here's the cool thing about the remainder theorem. It says you don't even have to do all the long division or synthetic division. It says that if you just plug in whatever this is equal to 0 for that k, so for like us up there, it was +2. It says if you plug that in, it will actually give you the remainder. Whoa, that's pretty cool. Check this out. Let's do it up here. Let's go up here and plug in what?
2.
2. Let's plug in our opposite, our 2, and use our order of operations. What is 2 cubed? 8. 2 squared? 4 times the -3. -12. 5 and 2 together multiplied is 10, and then -6. And notice if I grab the positives, that's 18. And if I grab the negatives, that's also 18, which gives us what?
Remainder is 0.
And if we have a remainder of 0, then we know it is a factor of our original thing. That's what the remainder theorem is saying. You could just plug in the opposite of that k, to your function and see if it's hopefully 0. And if it is, then guess what we get to call it instead of the remainder theorem?
The factor theorem.
Very good. Because if it's equal to 0, then what?
It's a factor.
Yep. That's the big difference between the two. Okay, this one says you can find any remainder, but this one says that if it is a 0, then it is a factor. So this one more powerful, but this one more inclusive. Okay, virtually saying the same thing. Right? So if I gave you something like this as an example, and I said, I want to know if this is a factor of it, what would you do?
Plug in 2.
Very good, just like we did before. And that would give me 8. 2 squared is 4, times 4 is positive 16. Negative 8, negative 16, and you can see all that, yep. Therefore, yes, this is a factor. If you wanted to prove it, you could do a quick little synthetic division, where I'm going to take the opposite of that, or where it gives me 0, which is positive 2, and then 3, 2, 1, 0. We're good. Take the coefficients, 1, 4, negative 4, negative 16. Bring the first thing down. There's my setup. Now watch how fast this can be. 2, 6, 12, 8, and then 16 to get my 0. There it is again. Which way do you like? Which way is faster? It really depends. Not only on the person, but also on the polynomial and the factor that they give you. Okay, the cool thing is, which one of these ways works? Both. Your option. As long as you show me one of those, I'm cool. Okay, and of course, you guys know, got to show me the work. Okay, so finally, to the last piece of this puzzle, what are we doing all of this for? To graph. And what are we trying to graph? Polynomials. And polynomials, unfortunately, look like this, don't they? They don't always come like this, all factored, where we can just set each one of those equal to 0 and start graphing. Okay, so what we want to be able to do to big, nasty polynomial functions is still find their zeros, still be able to factor. And this is the technique we use. It's called the rational zero or rational roots theorem. Because these solutions, these roots, these zeros that we're going to be finding are the key to this entire thing. Okay? And what we're going to do is we're going to focus on both the end and the beginning of this. And of course, not all of the other stuff and not even the x's. We're going to focus on the numbers, the coefficients of these things. Okay? So we're going to give those some names, since that's what we're going to focus on, rather than a sub 0 and a sub n. We're just going to call them p and q. All right, that way you guys can remember to mind your p's and q's when you're dealing with this. Okay, and we're going to always start at the end over the beginning. And how you can remember it's going to be the end over the beginning, think about a movie. What would you rather, if you had a choice, choose? Most people would choose to watch the end over the beginning. Okay? End over the beginning. Done. Right? So that's what we're going to have on these. And what that is going to give us is every possibility, which is good and bad. Doesn't mean that all of them are going to be roots or zeros or x-intercepts, but they are all of the possible options of them. Okay? And unfortunately, it is going to be every factor of both that leading coefficient and every factor of that ending term. that constant. Okay, so there's the how-to. Here's this fundamental theorem of algebra that basically explains it all in depth. All right, don't stress about too much of it. I wanted to at least show it to you because it says the fundamental theorem of algebra, right? Pretty important, obviously. But we'll talk about complex zeros and stuff like that more in calculus. Okay, in this class, we're focusing on some of the simpler versions of it all. But if I asked you, just like all the previous, to find the zeros of this, unfortunately, it's not factored. Now, who can tell me what is the maximum number of zeros that I could have for this polynomial?
Four.
I heard 4 and 3. If I was to set this equal to 0, how many solutions are possible? Max. Good, Jacob. Remember, that's what the degree tells us. There cannot be more than 3 x values that we would find. Okay? So those x-intercepts, those zeros, those roots that we're finding, okay? I know that there's a maximum of 3 of them. So that's good. But how do we use this rational zeros or roots theorem? All the possibilities are either positive or negative P over Q. And remember, we said that was all the factors of what? Go ahead, Bear.
And over the beginning.
The end over the beginning. And what did I mean by that?
4 and 2.
In this case, 4 and 2. Now, am I just going to put 4 over 2? Is that it? My only possibility is 4 divided by 2 or 2? Remember, it was all the factors of each of these. So the bigger and more even the number is, the worse it is. Okay, if it's odd or smaller, then less factors typically. So in this case, we're going to put 1, 2, and 4 up here. Those are all the possible factors of this P value we're calling 4. And the Q, beautiful, only 1 and 2. So what are all my possibilities? That's what this finds for us. All I'm going to do is I'm going to start with this, this, and this over 1. I'm just going to do one at a time. So plus or minus 1, plus or minus 2, plus or minus 4. Now I got that taken care of. Everybody okay there? Taking these and dividing it by that option. And now I'm going to do it by that option. So I'm going to first start by taking 1 over 2. Then I'm going to take 2 over 2, which I already know I have as an option. I don't need to write it again. Okay, don't repeat things and make more work for yourself. Okay, so that's out. And then 4 over 2, what's that? That's already there too. Yeah, very good. So in this case, these are all of our possible options, which is how many?
4.
Ah, actually, I got you. It's 8. Do you see why?
Plus or minus.
The negatives and the positives.
Sneak.
Now, we just learned 2 different ways to figure out if those are indeed zeros or factors. I just showed them to you. You guys hopefully are getting some of this. I know it's a long one. What do we do here? What are we going to do with these to see if they are indeed zeros? Roots. factors.
Plug them in.
Very good, Alex. That is one way. That is called the what theorem?
Remainder.
Very good. And what are we hoping that it becomes?
The factor theorem.
Which just means that our remainder comes out what?
0.
Excellent. Now, guys, do me a favor. Ladies, you can join in too. Which one of those are you going to choose to plug in? And remember, we can plug it in or we can do the synthetic division. Those are the two different ways that we saw that we could find whether they're zeros or factors or whatever.
1.
Heck yeah. I'm plugging in 1 all day, and not even -1, which is also easy, but 1 is the easiest because no matter how many times I have it to a power, it's still going to be 1. And when I multiply by 1, it's just going to be these coefficients. But to kind of write it out so that you can see what the heck we're doing here is I'm plugging in 1, and I know I'm going to get a 2 plus 5 minus 11 plus 4. And what do I really hope it is?
0.
Because then we have one of our zeros, one of our roots, one of our x-intercepts, and we can find the other. How many did we say there would be possible?
8.
8.
Good. 8 possibilities, but only 3 max. And since we may have already found 1, then we should be able to find the other 2 pretty easily. Good. So what does that give me? That's 7 plus, yes, 11 minus 11. There's my 0. Boom. I just found one of my zeros. Now, guys, now you have a choice to make. Do you want to sit here and plug in -1, and then 2, and then -2, and then 4, and -4, and then finally a half and a negative? Ugh. No, I'd rather not. Could you? Yes. But don't forget, some of these can actually be complex. Remember, the rational zeros only gives us rational possibilities. So as you keep graduating to higher level maths, you will possibly have higher level forms, which includes all in favor? Aye.
Aye.
Thank you, Julian. So at this point right now, I'm going to take what I already know, and that's that 1, and I'm going to use it to find what would be remaining. So I'm going to use my synthetic division. And I'm going to say, well, I already know that 1 works. And I'm going to check 3, 2, 1, 0. I'm good. I got everything accounted for. So now I'll just take all the coefficients. And I'm going to write down 2, 5, -11, and 4. And from there, I will then take that. I got to start somewhere. So I'll just bring the first thing down. And then I'll start multiplying and adding. 2, 7, 7, -4, and -4, just like we knew it should be. And so you're like, well, why are you doing that? That was easier than this. So that's why we did it this way first. But this doesn't give me anything other than the remainder. Where this gives me more. I knew I had the 2x cubed and some stuff, and I divided it by x minus 1, but I don't need that. So I knew that I was going to get a 2x here. All right, sorry, that was squared because that's cubed, and this is to the first. And then this was going to be x to the first, and then no x's, or just my constant. So I now have 2x squared plus 7x minus 4, and I want this and the other 2 solutions. Because guys, remember, I actually could rewrite this as this times x minus 1. But we already know that 1 is one of our solutions. All I would have to hopefully be able to do is factor that. And this trinomial, does it look factorable?
No.
Somebody's like, no, I never learned how to do with a 2 in front, right? It does look factorable to me because it's got the trinomial, and I'm just gonna unfoil, right? That's what factoring is. So I know it has to be a 2x and an x to get my 2x squared. I know it has to be a 4 here, but I have two options, either a 2 and a 2, or a 1 and 4, or a 4 and 1, right? So either one of these pairs. But I know that 2 and 2 cannot work because this would therefore have a GCF. And I know this doesn't have a GCF. So my only option is either 4 and 1 or 1 and 4. But again, for the same reasons, I know 4 can't be there because it would have a GCF again. So I know my only options are if I put the 1 there and the 4 there. And lastly, I need signs, both positives, both negatives, a positive negative, or a negative and a positive. Well, since this has to be a negative 4, I know they can't be the same. They have to be different signs. Because the only way to multiply 1 and 4 to get a negative is if one's positive, one's negative. And I know to combine to be a positive 7, I'm going to have the 2 times the 4 be positive, which would give me the 8x, and this be a negative to be a negative 1x. And does that give me my positive 7x? And this give me the factored version of that, which we said we would prefer. Because now, can you give me all the zeros or the roots to this thing? The x-intercepts? What are they?
1/2
1/2 and -4.
and 1.
Which we eventually would have gotten to. But I'd rather not just stick all of these in and plug them in. Because remember, every once in a while, you'll get things that are like this, x minus 6, right? Or x squared minus 6. And then you'll have to take square roots as answers. This doesn't give you that. It only gives you the rational possibilities. So you have to be able to use your, what is this called again?
Synthetic division.
In order to find the remaining piece that hopefully you can factor. And will you always be able to factor this? Of course not. But then what can you do with this? You can then plug in the other things to a simpler form than the original, because we already know that this is just the other part of that.
Real
Okay.
quick, how did we know 1/2 worked again?
We didn't know that 1/2 worked until we factored it. But if I set this equal to 0, I'd have to add the 1 over and then divide by the 2. Where here we can just take the opposite, Positive 1, -4. Well, this would be positive 1, but then we'd have to divide by the 2.
Gotcha. Okay, thank you.
Yep, no problem. Okay, and that's pretty much it for this. There's just some extra stuff that I wanted to at least show you and mention. And that's mainly for those types that we spoke about that were complex in nature, where they had that I involved. And what the complex conjugate theorem says, if you get a 0, a root that is complex, has a real and imaginary part, then it will always have its counterpart. its conjugate, where we only switch the middle sign. So that's cool. So if you ever found one of these, then you know that it has this. So you get to double up very simply. We won't deal with that in here, but I just wanted to mention for later on, so you have a leg up on people. All right. And then there's also this French dude by the name of René Descartes. All right. And he came up with this really cool way to figure out how many possible positive versus negative zeros. Up here, we didn't know. We just knew that these were all the options. So you can use this in this class if you wanted to, but it's not necessary. He says that if you just look at the polynomial as is, and you look at how many times that the signs change. So in ours, you look, it was a positive, positive, but then right here, it went from a positive to a negative, and then it went from a negative to a positive. So the answer is it changed twice. The signs changed twice. Well, then you have that many or an even number less positive solutions. And if you notice, we had 2. There could have been none. So it was either 2 positive or 0. That's what Descartes' rule of signs finds. Now you can also do that for the negative case, but you got to throw in a negative. So if I went back to my original and I made them all negative x's, a negative there, a negative there, a negative there, what would this be? Positive or negative? It's odd, right? It's cubed, so it'd be negative times that positive 2. The negative here would stay positive, so this would stay positive. Then the negative here times the negative would make it a positive. And then positive 4 is always positive. So now there's only how many sign changes?
1.
Just 1. Very good. Which means, according to this, if there's only 1, then again, it has to go down by an even number. You have 1 or, well, there has to be 1. So as you can see, we had 1 negative solution. Okay, so use that or don't, doesn't really matter. It's something just to kind of help you to get the correct answers. But that's it. That's all I got for you guys today. I'll go ahead and stop the recording now.